Hello, everyone. You can see my title, and this is also the title of my forthcoming book that's scheduled for publication sometime next year. You can find a fairly complete draft of the book, video lectures, a copy of these slides, and other material at my website. The purpose of the book is to provide a new conceptual framework for reinforcement learning and its connections with the traditional control methodologies of model predictive control and adaptive control. The book is based on visualization and geometric interpretations for the most part. On the other hand, there is quite a bit of mathematical analysis that is given in my earlier books that supports the visualization. So I'd like to start with two remarkable programs. The first program is AlphaZero, which plays chess and created a sensation when it came out in 2017. And the other program is much earlier, from 25 years ago. It's called TD-Gammon. And it plays backgammon. And at that time, it created a lot of enthusiasm about the prospects of reinforcement learning. Let me just, there is some noise in the background.
Yeah, if I can just ask everybody to mute their microphones while Professor Bertsekas is speaking. Thank you.
And now, Tigran, now Bertsekas is muted, unfortunately.
Okay, so now can you hear me?
Yes.
Can you hear me now?
Yes, perfectly.
Okay, very good. So I was talking about AlphaZero and TD-Gammon, and these two programs are very remarkable, even though they were quite a few years apart when they were implemented. They are quite similar. And both of them involve two algorithms. Some people don't quite realize that there are two algorithms that are involved in these programs. One algorithm is the offline training algorithm, by which the program learns how to evaluate positions and also how to select moves in given positions. And this is done with a lot of data, neural network approximations, and so on. The second algorithm is online play algorithm, which is what the program uses to play against other computer programs or human opponents. And it is based on multistep lookahead, rollout, and cost function approximations. And all of this has strong connections with dynamic programming, the classical method of policy iteration, and reinforcement learning type of approximations. And what I'm going to try to do in this talk is aim to understand this methodology so that it applies far more generally, and particularly on issues of how it connects with control system design, methods of MPC, model predictive control, and also adaptive control. But there are extensions in a broader context. For example, discrete optimization, integer programming, and the like, although I'm not going to talk about those in this particular talk. I'm having some, okay, I think I've got it back. Okay, I'm going to start describing the online play algorithm in AlphaZero, AlphaGo, and other related TD-Gammon and other settings. And then I'm going to discuss the offline training algorithm. Now, the online play algorithm is what you see here in blue, okay? The online play algorithm uses the results of offline training at 2 points. It uses a position evaluator to evaluate positions and a base player that it generates moves at given positions. So this is online play, but there is crucially used information provided by the offline training algorithm. And here, what we're trying to do is improve the base player, the one trained offline, by the following process. Given that we are at some position, let's say after k moves, the current position xk, we search forward for several moves through a look-ahead tree of moves and counter moves up to a certain depth. Then from the leaves of that tree, we simulate the base player for some more moves, and then we arrive at some positions here, which we evaluate using the position evaluator, and we approximate the effect of these future moves by using that evaluation. And now we back up these values back to the root, and we calculate a value of each possible move at the current position, and we play the best move. So that's what we do at a given position, and then we go to the next position after one move and do the same thing, and so on. Now, all of these programs use this structure, but there are differences. AlphaZero does not use this middle portion. It uses a very long initial portion. The look-ahead portion is very long and does not need to use this middle portion. AlphaGo uses a version of this middle portion. TD-Gammon relies very much on the middle portion because the look-ahead portion is short in TD-Gammon. TD-Gammon plays backgammon, which is a stochastic game, and the look-ahead tree expands very quickly. So it cannot use long look-ahead. So it relies on this middle portion, the truncated rollout. In fact, the term rollout was coined by the originator of TD-Gammon, Jerry Tesoro, and I'm using the term here in the same way that he has used it. There are also similarities with model predictive control. Model predictive control structures are remarkably similar to this structure and to the AlphaZero structure. There is an initial look-ahead portion where minimization takes place. This is called the control interval. And then there is sometimes a rollout portion, which is called the prediction interval. And then there's a terminal cost approximation. So model predictive control is pretty close to this structure, except some of the parts are implemented differently, because model predictive control deals with infinite state and control spaces for the most part, whereas these games deal with discrete state spaces. So let me go now into the offline training algorithm AlphaZero. It is approximate policy iteration with self-generated data. What we do here is generate a sequence of players. And the current player is used to train an improved player. And this process is repeated several times until we stop somewhere and we give the trained player at the end to the online play algorithm. So policy iteration has two parts every step: policy evaluation, policy improvement. These are done approximately with neural networks. So the current player is evaluated by playing many games, collecting data, and representing its evaluation by a neural network, which is trained with lots and lots of data. Now, once we have the evaluation of the current player, we can approximately improve the current player by using multi-step look-ahead minimization and an approximate form that's called Monte Carlo tree search. And the improved player, after we collect all this data from the improved player, we represent it with a policy neural network through training. So we have a sequence of value and policy networks generated here, and these are given at the end to the online player for use for online play. Now, TD-Gammon uses a very similar policy iteration algorithm for offline training using the so-called TD lambda method. It does not have a policy network. The functionality of the policy network is provided by using the value network through one-step look ahead. And it also does not use Monte Carlo tree search. And that's not really fundamental and does not really affect the overall character of the process. So here are some major empirical observations that I want to focus on. Here's the online player. It uses an offline player that has been trained with neural networks, but the online player plays much better in AlphaZero than the offline trained player. This is just a fact, and it's an obvious fact for people that have used these programs. The online player of AlphaZero is just a phenomenal chess player. By contrast, the offline player is relatively mediocre. And so there's tremendous performance improvement by having online play on top of offline training. TD-Gammon plays much better with this middle portion, the truncated rollout portion, than without the rollout portion. Tesoro had two programs in the 90s. The first one was in 1991, and it was based on this structure, but without the middle portion. Then in 1996, he introduced the middle portion, the rollout portion, and he found a great deal of improvement. The 1991 program was playing, his performance was subhuman. It was being beaten by the best humans. By contrast, the 1996 program had superhuman performance and has not been improved since that time. Now, these are empirical facts, and what we aim to do is to explain them, draw insights from them, and generalize them to other contexts by using abstract dynamic programming ideas, abstract Bellman operators, visualization for the most part to draw insight, and we will focus on the central law of Newton's method. This is the key new research that I'm going to present today, how Newton's method ties everything together. So here are the principal viewpoints of this talk. I'm going to show you that online play is just a single step of Newton's method for solving the Bellman equation associated with the problem, the dynamic programming problem. This is true for one-step look ahead. In the case of multi-step look ahead, the Newton step is preceded by some value iterations. In the parlance of numerical analysis, this is called a Newton SOR method. It's a well-known method with a lot of literature. SOR stands for successive over-relaxation. So online play is a Newton step. Offline training, on the other hand, provides the starting point for the Newton step. And in my opinion, online play is a real workhorse. Everything happens in online play. The big performance improvement is during online play. By comparison, offline training plays a secondary role. And a major reason for this is that online play is an exact Newton step. It does not involve approximations. It's not degraded by neural network training errors. So that makes it different and much more powerful. Now, the offline training can be done by many different methods. In reinforcement learning, we have temporal differences methods, aggregation, we have linear programming. There are many different ways to do the offline training. However, these differences and the various imperfections of these methods affect only the starting point, but they do not affect at all the Newton step, which is exact, and they're all washed out by the Newton step. The Newton step is a big equalizer. Errors that you may make in offline training are washed out by the Newton step. Now, there's a cultural difference between the reinforcement learning artificial intelligence community and the control community, particularly model ballistics and adaptive control. People in reinforcement learning focus primarily on offline training issues, whereas people in model predictive control are focused largely on online play and also stability issues, which are not dealt with by reinforcement learning community almost at all. So we're going to try to bridge this gap through these visualizations. And I'm going to talk a little bit about adaptive control, but instead of using the reoptimization in response to changes in the estimated model, we're going to use multi-step lookahead and rollout. This framework is going to involve an exact Newton step instead of reoptimization, but applied to a changing Bellman equation, changing in response to a system identification process. But the bottom line is that it's still a Newton step, and it's very powerful. Now, all of this applies in great generality. Abstract dynamic programming is a very general framework. It can accommodate arbitrary state and control spaces, stochastic systems, deterministic systems, hybrid systems involving both discrete and continuous state space and control space components, multi-agent systems, games and minimax, finite horizon, infinite horizon, discrete optimization, integer programming. Dynamic programming is a very, very general methodology, and abstract dynamic programming captures this generality. And because everything I'm going to talk about is couched on the abstract dynamic programming framework, it has very broad applications. Now, some of these viewpoints may be a little controversial and personal, so I thought of showing you this cartoon. These two people look at the same number, and this guy says it's a 6. But this guy insists it's a 9, and I think this cartoon may have some relevance to my talk today. So let me give you an outline. First, I'm going to talk about discounted and undiscounted infinite horizon problems to provide some context. Then I'm going to talk about abstract dynamic programming, abstract Bellman operators. Then I'm going to show by visualization how online play can be viewed as a Newton step. Then discuss stability issues, the region of stability and how you can visualize it. Visualization of rollout, truncated rollout, and policy iteration. Then I'm going to talk about a familiar problem, the classical linear quadratic problem, where the visualizations are in terms of Riccati equation operators, as opposed to Bellman operators. Then I'm going to discuss application model predictive control and the connections there, and then also adaptive control, indirect adaptive control with model estimation. So let me start with discounted and undiscounted infinite horizon problems. So what we have here is a system, discrete time system, excuse me, involving a state, which I denote by xk, it's a state of time k, a control uk, and a random disturbance. Wk is random, and the system evolves according to this equation. And we're interested in stationary policies that map state into controls, and this control must satisfy control constraint for every x. There is a cost for its transition, encoded by this function g, and the cost is discounted by a factor alpha. Alpha could be less than 1 or could be equal to 1. And at stage k, the cost is discounted by alpha to k. And the cost of a policy starting from some initial condition x0 is just a limit of the end stage cost. This denotes expected value over all the w's. This is a random variable, and we take this expected value and take the limit as the number of stages n goes to infinity. So this is a function. For every state, there is a value here given by this function, and the optimal cost function is obtained by minimizing overall policies, the policy cost functions. And I have in mind primarily three contexts. One is discounted problems where alpha is strictly less than 1 and g is bounded. This is the nice case. Everything I'm going to talk about is correct for discounted problems. Now, for other problems, there may be exceptions, and I'm going to mention a few of those as I go along. The second class of problems is stochastic shortest path problems, where there's a special cost-free termination state. Think of the origin as being a termination state, and alpha is equal to 1. And then the MPC type of problems, where the system is deterministic, the cost per stage is positive, the origin is the termination state, and this is a regulation problem. The aim is to drive the state to the origin or keep it close to the origin, and this is encoded in this positive cost. The cost is 0 at the termination state, positive everywhere else. So these are the problems I have in mind, and let me give you a synopsis of the theory. The first result is that J star, the optimal cost function, satisfies Bellman's equation. Now, there is one such scalar equation for every state. So this is a functional equation. And J star satisfies this equation, often uniquely, but not necessarily. That's why I have these question marks. There's an optimality condition. If for a given x, mu stars of x attains the minimum in this equation for every x, then the policy that you obtain is optimal. Again, there are some exceptions to that. And there are, regarding algorithms, the first major algorithm is value iteration. It generates a sequence of cost functions starting from some J0, which can be more or less arbitrary, and uses this recursion here, this iteration, which is just the right-hand side of the Bellman equation, but with jk minus 1 replacing J star. This generates a sequence of finite horizon costs, it's one of the major algorithms. The other major algorithm is policy iteration, generates a sequence of policies, mu k, and their cost functions. Mu 0 is arbitrary. The typical iteration starts with some policy mu and generates a new policy, mu tilde. I'm going to be using these symbols a lot in this talk. Mu for current policy, mu tilde for the next policy. In two steps, there's a policy evaluation step that computes the cost function J mu, and there is a policy improvement step that calculates the improved policy by using this equation here, by doing for every x this minimization, which is the same minimization as in Bellman's equation, except that we use J mu, the cost of the current policy, in place of J star. Okay. So now let's talk about approximation in value space, a major approximate dynamic programming reinforcement learning framework. Here we act, it's very difficult to find J star, so we replace it with an approximation, J tilde, in Bellman's equation. And when we arrive at a state X, we perform this minimization, which balances the cost of the first stage plus the future cost as evaluated using this J tilde and also appropriately discounted. This minimization is over all the possible controls at the given state and provides a control to use. So we apply this control and then we go to the next stage. At the next state, we do the same this type of minimization again, and we proceed going forward. This is called one-step look ahead because we look forward only one step before going to the approximation. Multi-step look ahead is sort of the same thing, except that we minimize the cost of the first L stages plus the future cost as evaluated by J tilde. And now this is an L-step problem. And it involves minimization overall control UK and policies from K plus 1 to K plus L minus 1. We solve this problem and we use at XK this first control and we throw away all the rest. Either way, one-step look ahead or multi-step look ahead, this defines a look ahead policy. Mu tilde of XK is the control that's obtained from this minimization. It's the minimizing UK. I'm going to be using a lot of these symbols. J tilde is cost approximation. Mu tilde is the look ahead policy obtained by either one-step look ahead or multi-step look ahead. And here's the key fact. J mu tilde, the cost function of the look ahead policy, is a result of a Newton step for solving Bellman's equation starting from J tilde. Now, this is true for one-step look ahead. For multi-step look ahead, L greater than 1 is the result of a Newton SOR step, which is some value iterations followed by a Newton step. Either way, the error decreases superlinearly. That's a generic and the key property of Newton's method, whereby the errors that diminish very rapidly, and in particular, this ratio goes to 0 as J tilde gets too close and tends to J star. So you had an error in cost between J tilde and J star, and you have a new error after the Newton step that gives you the cost of the look ahead policy compared with J star. And this numerator is tiny relative to the denominator. These errors reduce very fast superlinearly. So now let me go into abstract dynamic programming concepts and how you interpret all this in terms of Bellman operators and through visualization. Okay, so here's the Bellman operator. It's the right-hand side of what you have in Bellman's equation, and it maps cost functions J into cost functions T mus of J. So J has a component for every X. T mus of J has a component also for every X, and it's given by this expression involving the cost of the first stage using mu and the cost of the remaining stages as measured by J. So there's one such equation, a scalar equation for every X, and I call this the mu Bellman operator. And there's also the min Bellman operator, which is the one that appears at the right-hand side of Bellman's equation, and it involves minimization here over all controls. And if you take this values here and minimize over mu, what you get is Tj's of X. Again, J is a function of the state. Tj is also a function of the state. So this is a functional, this is an operator mapping functions into functions. And Bellman's equation can be written in shorthand by using these operators. The min Bellman equation is represented as a fixed point equation. J star is a fixed point of T. And there is a Bellman equation for every policy. J mu, for a policy mu, J mu, the cost of that policy is a fixed point of this mu Bellman operator. So T mu and T transform real valued functions J into functions T mu of J and T sub J. And for this talk, I'm going to assume that these are real valued. Now, these are pretty big operators. How many dimensions do they have? Well, for every X, there's a scalar equation. So the dimension is the number of states. It could be astronomical or it could be infinite. On the other hand, for every x, these are real valued functions of j, and you can view them in for a single state. Okay, as an example, suppose you have a two-state system. Then j is a two-dimensional vector, j1, j2. This is a real number, this is a real number. This is a vector in R2. And T sub j has two components. It's also a vector in R2, the components tj's of 1 and tj's of 2. So even for a two-state system, we have an operator that maps two-dimensional space to two-dimensional space, so you need a four-dimensional graph to represent it. That poses a little bit of a problem. Mm-hmm. But on the other hand, even though T mu and T are large and perhaps difficult to visualize, look at first sight, they have some nice properties. The first is that they are both monotone. As you increase uniformly the j function here and here, T mu sub j and Tj also increase. The reason is that the expectation preserves monotonicity. Expectation means a positive linear combination, so it has the monotonicity property. And similarly here, as you increase j because of the monotonicity, because of the expectation operator preserves its monotonicity, and the minimization also preserves monotonicity, you have that T mu and T are monotone. As another important fact is that T mu is linear. Okay, expectation is a linear operation, so this is a linear operator. T, on the other hand, is concave. It's concave because it can be viewed as the minimum of linear operations. If you take the minimum of linear operations, then you get something that's concave. So in particular, for every fixed state x, Tj's of x is a concave function of j, not of x, of j. J, remember, is a function. T sub j is also a function of j that's concave in the traditional form, in the traditional meaning of convex analysis. So for infinite dimensional state space, T mu and T are infinite dimensional operators, mapping an infinite dimensional functions in the function space into itself. So now the question is, how do we deal? We want to do visualization with these operators. How do we do that? Okay, so what we do is use one-dimensional slices of the graphs of these operators. To give you an idea of this, let's consider a two-state and two-control example. We already have a four-dimensional graph, but we can represent as two three-dimensional graphs. And I'm going to do it here. Okay, blue stands for the mu operator, and red stands for the min operator. Here is the T mu operator, and it has two components, one for state 1 and one for state 2. And I'm showing these components here for state 1 and for state 2. And this is linear and monotone, and this is concave and monotone. So for state 1, there are two controls here. Each control defines has a linear graph. It's the blue graph that you see here. Here is J1, J2, and this is the linear function T mu sub j's of 1 for state 1. Now, the min Bellman operator is obtained by minimizing over these two. So it's a piecewise linear function. It has this red graph here that you see. It's a function of J1 and J2. And I'm showing also J star here. J star is shown right here. And I want to focus attention on the fact that we can consider slices, one-dimensional slices that go through J star, and you can see this slice here. By using one-dimensional slices, we're able to visualize this operator on a piece of paper rather than and deal with a high dimensionality. So there's a slice like that for state 1, and there's also a slice like that for state 2. And the slice involves a piecewise linear monotone function. You can see the 45-degree line here. And so that's a visualization for a 2x2 problem. And from now on, we're going to be focusing on one-dimensional slices that pass through J star. Okay, so let's visualize the new Bellman operator. It's given by this equation. The mu Bellman equation is this. J mu is a fixed point of T mu. And the operator has a linear graph. It's this blue line that you see here that defines T mu of J as a function of J. And to find the cost of mu, J mu, I have to find the point where this blue line meets the 45-degree line. And this is the fixed point of the operator T mu. And it is the cost of mu, satisfies the Bellman equation. Of course, this cost has to be somewhere further to the right of the optimal cost. And all of these costs are to the right. There are many of these mu operators, and they're defined in a similar way. Okay, now the min Bellman operator. The min Bellman operator is obtained by minimizing overall controls or minimizing overall these blue operators for a given x. It's concave and monotone, and it's defined as follows. Here is T sub j, this red graph here, as a function of j. And to obtain its value, let's say at some point j tilde, we have to consider all the policies, find the point of intersection of these policies with this vertical line, and go to the lowest point. This is the minimum over policies of T mu of j tilde. So that's how you find T of j tilde, and you do the same for every j. And basically, the red curve is the lower envelope of the blue lines. You have all these blue lines, and what lies below that is the graph of the min operator. And now the optimal cost, J star, is obtained as the fixed point of this of the operator T. It is the point where the red curve meets the 45-degree line. So that's how you visualize J star and all these operators and the connection of the blue operators with the red operator. I think to notice is that the red operator is concave. And also at J tilde, the blue operator that attains the minimum is tangent, provides a linearization of the red operator at this point. Now, this linearization is going to be key for understanding the role of Newton's method. So let me also illustrate how value iteration can be viewed within this operator context. We have T sub j as a function of j. And in value iteration, we generate a sequence of cost functions. We start with some j0, and we find tj0, okay? This is j1. Then we reflect j1 across the 45-degree line to this point here, and then apply t to it, and we obtain the second iterate, j2. So j2 is t squared j0. We reflect it again across the 45-degree line, and we obtain J2, I'm sorry, J3, and so on. So there is this staircase construction that provides a visualization of value iteration. And you can see that there's a tendency to converge to the fixed point, but not always. It depends on what J0 is, the slope of T. In particular, if T is a contraction mapping, which means that the slope is uniformly less than 1, then you get convergence, and you get also a unique fixed point. But that's the favorable case, but that doesn't always hold true. So that's the visualization for value iteration. And now let me go into Newton's method and its connection with online play and one-step look ahead. Okay, so let's look at the familiar Newton's method for solving a fixed point problem, finding a fixed point of the operator T. This is a generic operator here, and I'm showing it in red, concave and monotone as it is in dynamic programming. And Newton's method is an iterative method. It generates a sequence of iterates, JK. You start at J0, generate J1, J2, and so on. At the typical step, you are at JK. And what you do is you linearize T at JK. And this blue line is the linearization. It involves the first order Taylor series expansion of T at the point JK. We now solve the linearized fixed point equation. In other words, we find this point here, and that's the new iterate JK plus 1. So that's what Newton's method does. And it's pretty similar to one of the things I showed you earlier for online play and for one-step look ahead. So JK, linearization, solve the linearized problem, JK plus 1. Then linearize at this point, solve the linearized problem, obtain JK plus 2, and so on. And you can see that this process can be very fast, indeed quadratic, under the right conditions. Okay, I've shown also here T to be differentiable, but then we will relax this assumption in what follows. So this is generic Newton's method. And here is how it relates to one-step look ahead. Now, in one-step look ahead, what we do is we have a J tilde, a cost approximation, and we find mu tilde, a one-step look ahead policy, which is obtained by minimizing overall possible policies. So what one-step look ahead does is it linearizes T at J tilde and obtains this blue operator, which is the look ahead policy mu tilde. So how do we represent the cost function of this look ahead policy? Well, it is simply the intersection of this blue line with the 45-degree line, and it gives you J mu tilde as the fixed point of T mu tilde. So we start with this cost approximation, and we end up with this one-step look-ahead policy cost. And you can see that it is an honest-to-goodness Newton step. Now, it's a key insight, but then immediately some questions arise. In the classical form of Newton's method, you have to have this T operator be differentiable, once differentiable. Do we need that? Well, the answer is no, you don't need that. You can substitute concavity and monotonicity for differentiability. This is known in numerical analysis. If you look at the classical books like Ortega and Reinbold from the 60s, there is theory associated with that, primarily with monotonicity. But it's also true that you don't have to have differentiability here. Concavity is sufficient because this blue line, in the case of a non-differentiable operator is just a subgradient. You use subgradients instead of derivatives and gradients. And the important thing is that you have a tangent hyperplane, a supporting hyperplane. And this can be provided by a subgradient or by a gradient just as well. Now, you do need some assumptions for this process to be valid, because there are all sorts of anomalies that can occur here. But everything works out fine for contractive problems, such as the discounted problem that I gave earlier. And notice one more thing. The Newton step is very fast, has superlinear convergence, so it smooths out starting point variations. If you make variations to J tilde, there will be corresponding variations to J mu tilde, but these variations are tiny relative to these variations. So you may make some errors here, and these are smoothed out by the Newton step. And there's lots of empirical evidence to support all this. Okay, now let me go into stability issues and how we visualize them. Here I'm going to be focusing mostly on the MPC context, deterministic system, cost-free terminal state, and so on. So stability is of paramount importance, of course, in MPC, but the question arises, how do you define stability, given that the state space can be discrete and can be continuous? So instead of going to concepts of Lyapunov stability and the like, we adopt an optimization-based definition of stability, and we say that a policy is stable if its cost function is finite for all x. If the cost of the policy does not blow up for any initial state, then we say that the policy is stable. And this has the advantage, it's a very general definition. And generally, this is true if T mu is a contraction or has slope less than 1 in the context of our figures. So let's look at one step look ahead. We want to, the region of stability we define to be the set of all J tilde cost approximations for which the look ahead policy is stable. So you can see here that if you choose J tilde to the right of some threshold, then the corresponding policies, because of the monotonicity, are stable. On the other hand, if you choose them to the left of some threshold, the policies are not stable because they don't intersect basically the 45-degree line. They have slope greater than 1. And the threshold is precisely the point where the Bellman operator has as tangent the 45-degree line. So this is how the region of stability is demarcated. J tilde to the right of this threshold point gives you a stable policy, and otherwise it's an unstable policy. Of course, this is for a one-dimensional slice. For a multi-dimensional case, it's more complicated than that, but the general idea still applies. Now, this is for one-step look ahead. For multi-step look ahead. Now, multi-step look ahead tends to push J tilde into the stable region. Now, remember that multi-step look ahead amounts to some value iterations and then taking the Newton step. So this gives you an example where a two-step look ahead. So what are the stable J tilde? The ones that after you perform one value iteration, you cross into this stable region for one step look ahead. So the threshold moves to the right and the region of stability is expanded by multi-step look ahead. And there are rigorous studies, mathematical analysis that verify this. And it's also a known fact in MPC. So it makes sense to push J tilde towards J mu, which is stable. And that's what this multi-step lookahead does, and it's also an idea that underlies the concept of rollout. So now let me go into rollout and policy iteration and how we visualize them. Okay, now rollout is simply a Newton step starting from J tilde equal to the cost function of a policy. So you have some policy mu, which we call base policy. It has an evaluation, okay, obtained by this intersection point. This is J mu. And then rollout does a Newton step, linearizes here, and this gives you the rollout policy. So that's simply what it is. And it can be implemented in a number of ways, including simulation. And an interesting fact is that if you have a stable policy to begin with, then the rollout policy will also be stable. You can see this from this figure. Now, policy iteration is simply a repeated rollout. You start from a policy, do a rollout on it, and then do a rollout on the rollout, and so on, and generate a sequence of policies. The visualization is the following. Let's say mu k is the current policy, and this is its evaluation, the cost of mu k. You do a Newton step, linearize the Bellman equation at j mu k, then obtain mu k plus 1. This is the policy improvement step, policy evaluation, policy improvement, and obtain a new policy, and its cost is obtained by the new policy is this corresponds to this blue line, and its cost is obtained by projecting on the horizontal this point of intersection. So start with mu k, generate mu k plus 1, then generate mu k plus 2, and so on, and converge very fast. The pure form of policy iteration is exactly Newton's method and does not rely on differentiability at all. The fact that the connection with Newton's method actually is well known in control theory, starting from Kleinman's paper on linear quadratic problems. Kleinman was a student of Mike Athens at MIT and wrote this paper that was followed up by a lot of other works, both for linear quadratic problems and also for more general forms of policy iteration. There are also corresponding results in the Markov decision process theory. All of this is very well known in dynamic programming, as well as linear quadratic problems and the like. Okay, so now let's go into truncated rollout. Rollout is a single step of Newton step starting from the base policy. Truncated rollout starts from some j tilde, does several value iterations using the mu operator, and then at that point takes the Newton step. So it is first value iterations with the mu operator, m of them, m equals 4 in this particular figure, starting with some j tilde, and then applying the Newton step by doing this minimization here. And that's the cost of the truncated rollout policy. So truncated rollout also involves a Newton step. Now you can have a combination of L-step lookahead minimization and M-step truncated rollout, and the total lookahead is L plus M. And an interesting fact, it is that the sum that's important, not so much the individual values of L and M, but the sum is important. Now, rollout with a policy is much cheaper than lookahead minimization. So truncated rollout can be viewed as an economical substitute for multi-step lookahead. And this was the motivation of Tesoro when he introduced truncated rollout in the context of backgammon. Also, people use this rationale in MPC, use rollout with some base stable policy to to enhance the starting point for the Newton step. So now let me go into a familiar problem for people in control, the linear quadratic problem. In linear quadratic problems, there are similar visualizations, but instead of using the Bellman operator, we use the Riccati equation operator. So in this particular, for illustration, I'm using a one-dimensional linear system with an A coefficient and a B coefficient, a quadratic cost involving non-negative Q and R coefficients, and alpha equals 1, no discounting. And it is well known that the optimal cost function is quadratic with quadratic coefficient K star, and this K star solves the Riccati equation. And the Riccati equations are fixed point equations, the algebraic Riccati equation, and it's given by this expression here, involving A, B, R, and Q is concave, and the solution of the Riccati equation is obtained by intersection of this 45-degree line and the red graph here. Actually, there are two solutions. However, there's a unique solution that is positive, and this other solution that is not positive. In fact, this is true for multidimensional problems. The normal case is when Q and R are positive, and K star has its unique positive solution. However, just to sensitize you to exceptions, here's an exceptional case where Q is equal to 0. And now, in that case, you lose observability, but K star is actually equal to 0 because there's only constant control, and you can set the control to 0 and attain optimal cost to 0. However, the Riccati equation has two non-negative solutions, and there's another solution here which has an interesting interpretation. And this is an example where you don't have the uniqueness. And in fact, if you try value iteration for this exceptional case, you'll find that value iteration converges to the non-optimal solution rather than K star. This is just an example of exceptional behavior, and there are many of those in other contexts that are more complicated than linear quadratic. Okay, so here's a common question. In the end, I want to have a policy, and we say that this online play policy is good. Why can I not learn this policy by some neural network and use it? In fact, there is a whole community in reinforcement learning that practices approximation in policy space, where we don't care about cost function approximations, multi-step look ahead and the like, but instead we parameterize the policy and we optimize the parameters by using some kind of training, perhaps neural network training. There are methods called policy gradient methods, random search methods, and so on. There's a wide variety. It's a very broad field. And my visualizations and my point of view suggest that this viewpoint is flawed because it lacks the exact Newton step that sort of does all the magic. It corrects all the errors of offline training and superlinearly so. So there's no correction mechanism in this approach whereby we don't use a Newton step. And to illustrate this point, I have an example here. It's a one-dimensional linear quadratic example with a known and fixed model. And we consider a parameterization of the policy. We use linear feedback policies with coefficient L. And L, we vary L, okay? This is the L, we vary it broadly. Okay, L around minus 0.4 is optimal. And what I have plotted here are the cost differences from the optimum. Without the Newton step, just this policy, apply this policy, we see that very quickly the performance of the policy is degraded. On the other hand, if you introduce one step look ahead, in other words, if you introduce a Newton step, then the performance is almost indistinguishable from the optimal. So all this is the loss that you incur for not having a Newton step to correct the errors in the suboptimal policy parameterization. Let me say a few things about model predictive control. Well, I'm not doing very badly with time. I'm glad about that. So I'm going to go a little slowly here. Okay, model predictive control is a major methodology, perhaps a dominant methodology in control theory research these days. It dates to close to 40 years and has extensive literature. It has been applied to very, very challenging problems. There's a lot of experience with it. The classical form of MPC applies to continuous state and control problems, deterministic problems, with positive cost. So we have a nonlinear system and a cost function that's positive everywhere except at the origin, where the cost is zero. So basically, this encodes our desire to drive the system to the origin and keep it there. Now, MPC is culturally different from the reinforcement learning artificial intelligence practice of sequential decision making. The architecture of MPC, as I mentioned earlier, is very similar to AlphaZero. It includes lookahead minimization, which is often called control interval. In some versions of MPC, there's a so-called prediction interval to improve the terminal cost approximation, and there is which amounts to rollout with some stable policy. And there is also a terminal cost function that's being used. So all the elements are there. On the other hand, MPC focuses on continuous space applications and also stability issues, and also relies primarily on online play. There is some offline training in MPC, for example, computing offline terminal cost approximations, computing some stable policies to do rollout with, and also computing target tubes, safe regions, in order to deal with state constraints. One of the central motivations of MPC is to be able to deal with state constraints, critical state constraints, that for which the linear quadratic unconstrained framework does not deal very well. So to do that, there are some interesting issues of how to use controls, to select controls that keep you within the safe region. And there's a theory of target tube reachability, which actually is very dear to my heart because my PhD thesis 50 years ago dealt precisely with this topic of introducing the notion of target tube and also how you construct these target tubes. Nobody read my thesis for about 15 years, but then all of a sudden through MPC, it became an interesting topic. Okay, so this is the classical form of MPC, but there are a lot of extensions. And you can look at, for example, the recent books by Rollins, Main, and Deal, and Borelli, Bemporad, and Morari, which describe a lot of extensions that deal with stochastic uncertainties, hybrid systems involving both continuous and discrete control and space components, minimax versions, deal with target tubes, and so on. So there's a lot of very broad literature dealing with a broad variety of problems. Moreover, more recently there has been some emphasis on using data, simulation obtained data and roll out with some offline trained policy. And this comes under the general name of learning NPC. This term was introduced in the paper by Rosolia and Borelli, who have done interesting work in this area. And there has been also a recent paper by Yuchao Li and Johansson and Martinson, professors at KTH, and I'm also a co-author in this paper. So now let me go into adaptive control with model estimation. What's called indirect adaptive control is combined identification, model identification, and adaptation of control in response. So what we have here is a system that's changing over time. Its model is changing over time. Data is collected from this system, and we run a model estimation, system identification algorithm, the results of which are passed into an adaptive controller who makes proper adaptations. And the indirect adaptive control viewpoint is to re-optimize the controller when the estimated model changes. On the other hand, there's a problem with that. This re-optimization may be difficult or very time-consuming. So there is room for simpler alternatives. And rollout provides, and rollout combined with multi-step lookahead provides such an alternative. You use multi-step lookahead that takes into account the current model as estimated by the system identification process, but the rollout itself uses some robust policy. However, all of this involves a Newton step. So we use a Newton step instead of re-optimization. And if you're close, if your changes from the nominal are not very serious, then the Newton step, I argue, is just as good as re-optimization and computationally simpler. So we capitalize on the fast convergence of the Newton step to avoid expensive re-optimizations. So that's the idea for the use of rollout in adaptive control as a substitute to re-optimization. And let me give you an example here. This is a one-dimensional linear system, and it involves an unknown parameter, a changing parameter B, and R result may also be variable here in the cost function. Now, as B changes, the optimal cost as measured by the quadratic cost coefficient changes. If you use a fixed policy, in particular, the policy that is optimal for the nominal values of B equals 2 and R equals 0.5, then the performance degrades. So robustness is not really fixing the problem here. If you have large deviations from the nominal parameters, then you can get a lot of degradation of performance. On the other hand, if you use rollout, including the Newton step, there's hardly any change from the optimal. It's just as effective as re-optimization. And this is true when we change B but keep R fixed, and the right figure, we change the cost parameter, the R, and keep B fixed. So this is what I want to say, that using a robust control as a base policy without the Newton step is often flawed. And we correct the flaw by introducing the Newton step. Okay, let me conclude. I want to make a few points here. The first one is that there is much to be gained by using online play on top of offline training. There's a potential for very large improvements. If you just use just offline training without online play, it may not work very well because we lack the Newton step that corrects for training errors and can deal with changing system parameters. On the other hand, using just online play without offline training, we may miss out on performance because we will not have good starting points for the Newton step. So that's the first point I want to make. The second point I want to make is that Newton's method is central in all this. This is a new insight and can guide both analysis, explain behavior, and provide motivation for new algorithmic designs. And again, the Newton step is exact. All the approximation, neural networks and the like go into the starting point for the Newton step, which washes out training method differences and errors. Another point is that there's a cultural divide between reinforcement learning as practiced by the AI community and the control community. We are dealing with very similar problems using similar methods, and the cultural differences can be bridged by combining offline training and online play in the model of AlphaZero. MPC uses a very similar architecture to AlphaZero, but can benefit from RL and artificial intelligence ideas. And we can also approach indirect adaptive control through rollout using a Newton step in place of reoptimization. The last point I want to make is that all of this is very general. Even though I focused on just a few problem types, the generality comes from having arbitrary state and control spaces and the generality of abstract dynamic programming. And in particular, there are a lot of interesting applications in discrete optimization, integer programming, multi-agent versions, which involve exploitation of the special structure. And a lot of this is in my 2020 book, the details of that. Finally, there are exceptional behaviors all over the place once you get away from the benign discounted case. And there's a lot of room for clarification by mathematical analysis and computational experimentation. So let me close with some words of optimism. We had tremendous successes in both artificial intelligence reinforcement learning and MPC. And this provides hope for the future. More success can be expected by bridging the gap between these two communities. Lookahead minimization and rollout can be a computational bottleneck. And people in both artificial intelligence and MPC have been struggling with that. On the other hand, we have massive computational power through distributed computation. A lot of these computations can be parallelized, and all of this power can mitigate the computational bottleneck. And so we can obtain online strategies that are more sophisticated as a result. So all in all, the future looks very bright. And I thank you very much for your attendance.